Okay, so now let's look at how to analyze a conductivity graph. So a conductivity graph, basically, as a titration is being done, a conductivity meter is put into the analyte. And so that allows the conductivity of the solution to be monitored over time. And basically, the idea is that if we're starting with an acid or a base, doesn't matter, but whatever we're starting with as the analyte, then what we actually have there is ions in solution. And so because we have ions, we should have some sort of a reading of conductivity. And obviously, the stronger the acid or the stronger the base, the more ions we have because they've been completely dissociated in the water or in the solution. And then as the reaction starts to take place and neutralization starts to take place, those ions are slowly removed from the solution. And so as those ions are removed from the solution, where we would expect our conductivity should drop. And that's because as those ions are no longer there, we're not able to conduct the electrical current. And so we see a drop in that conductivity. If we come past the end point or past the equivalence point, and now we're in excess of whatever the titrant is, again, we should see an increase in our conductivity as there's now more ions in the solution again. And so this is what a conductivity graph looks like. So same as our other graphs here, we're looking at our starting conductivity. Okay, so instead of being pH for these graphs, we're looking at the conductivity, and it's again over or as a function of the volume of the titrant added. So in our conical flask or our beaker where our analyte is, this is our initial starting conductivity. As we add the titrant and the reaction starts to take place, we see a drop in the conductivity, okay, and this is heading towards the endpoint. At C, this is where there's a drastic change in the conductivity, and so C is where our equivalence point is. Okay, so rather than being able to see an endpoint with a color change, what we can actually see is that drastic change in the conductivity, and that's what's going to give us our equivalence point. Okay, so rather than a color change, we have a change in conductivity. And then as we continue to titrate, we end up with more ions back in the solution, and that means that our conductivity is going to increase up here where D is. So now I'm going to show you some examples, and I've also included these as student worksheets. So when you're in the classroom, you can use these exact same worksheets with your students if you wish. All right, let's look at our conductivity graphs. So in this first one, we have high conductivity, and let's just for now assume that we're always starting with an acid. So we're going to say that this is quite a strong acid. We have a high conductivity. So we're going to have some sort of an acid that is quite strong so that all of the ions have dissociated. So as we add, so this is going to be a strong acid. And it's being titrated against a strong base. So if we look past this equivalence point and keep going up, we can see that we actually also end up with something that has quite a high conductivity. So that means we've also got a strong base. Now our equivalence point happens where these lines continue, so where they cross over. So if we treat this as a separate line, so basically this is looking at our acid in solution, okay, and this is looking at our base in solution. Where that crossover point happens, that there is our equivalence point. In this example here, we're still starting with a strong acid, but as you can see here past that equivalence point, we actually don't go up as high. So we're ending up with a base, we're titrating it with a base that is not as strong. So here we would say we have a strong acid and we have a weak base. And again, here is our equivalence point, and we can work out what the volume was if we had a scale there. Now with these examples down here, they work a little bit differently. So here we're starting with a weak acid this time, and we're ending up with a strong base. But they're not the same as the previous examples because they're not just straight lines. We actually have a dip here. Now, the reason for that is because we're starting with a weak acid. What we actually end up with is a small amount of the hydrogen ions that bind and create water. And so that sort of, they create these water molecules, and because they're taken out of ions or out of solution, we see a dip in the conductivity here. Okay, but as we continue to titrate, it changes direction, okay? And we actually end up with an increase in the conductivity. And the reason we see an increase is because that we have this substitution of the weakly dissociated acid with whatever the base is. And so the equivalence point here is actually not down at the dip. It's in this, again, the change. We're looking for that drastic change. And so if we were to continue our lines out here, okay, that is our equivalence point. And so we could bring that down to work out what the volume of the titrant was at that point. So again, over on this one here, we have another weak acid, but we have also a weak base. Okay, so we can see that the conductivity doesn't rise too much after that equivalence point. And again, here our equivalence point is a little bit over that way. Okay, and we can work out what the volume was at that equivalence point. So key things that students need to be able to do is to identify whether they're starting with a strong acid or base, and to be able to say that the reason they can tell it's a strong acid or base is because it's got high conductivity, because we know that a strong acid is completely dissociated in water. Whereas the weak acid, because it doesn't fully dissociate in water, we end up with a dip before it starts to rise again as we're adding in the base. Okay, and so adding in a strong base where the ions are almost all dissociated is going to increase our conductivity of the solution. And again, we're looking out for that sharp change in the conductivity, and that's how we know where the equivalence point is.